In this section, we're going to take a look at the extrema of a function of two variables. So let's begin with a definition. Let f x comma y be a function defined on a region R which contains some point which we'll call x naught comma y naught. Then the function f is said to have a relative maximum at the point x naught comma y naught if for all x and y in a neighborhood disk of radius epsilon greater than 0 about the point x naught comma y naught, we have that f of x naught comma y naught is greater than or equal to f of x comma y. This may seem a little convoluted, but basically it's saying, you know, you have a relative maximum at that point if for all the points that are nearby that point is still higher. So you have a function of you have a function of two variables, so that's going to be in space. You have a function that's defined over some region here. You have a relative maximum at that point because if you look at all the points that are nearby that point, they're all less than or equal to that point in height. And so here, if you project that point down onto the domain, there's some little neighborhood of some radius epsilon. We don't know what epsilon is, but it's just some positive number, probably small, but whatever. And for every point in that neighborhood around, notice that that point is higher than anything around that neighborhood. Note this does not have to be the highest point of your entire function. For example, you might have something that looks like this. And here, this would still be a relative maximum because even though it's not the highest point of the entire surface, it's still higher than all the points nearby. This would also be another relative maximum. So note that you can have more than one of each. More than one of each relative maximums or relative minimums, which we can define similarly. The function f has a relative minimum instead of relative maximum. We have a relative minimum at x naught comma y naught if for all x and y in a neighborhood disk of radius epsilon. And again, we don't really worry about what epsilon is, just some positive number. About that point, x naught comma y naught, then f of x naught comma y naught would be less than or equal to f of x comma y. So exactly the same thing, but reversed. It's a minimum if all the points nearby are bigger. It's a maximum if all the points nearby are smaller, in keeping with the typical meaning of minimum and maximum that we may be used to. Okay. Now, we have a theorem that shows us how to find maximums and minimums. Let's begin with a function that is, let f of x comma y be a continuous function defined on a closed and bounded region. It's bounded, it doesn't go on forever. It's closed, meaning it includes all of the endpoint, all of the boundary points. So here, all we're saying is our domain doesn't go on forever. It's got a clear boundary around the domain. So f of x comma y is a continuous function that's defined on a domain that's clearly demarked and bounded and such. It doesn't go on forever. We'll call that region R in the xy plane. Then, two things. First of all, there exists an x comma y in R. There exists some point somewhere in that region such that f of x comma y has a maximum value. And two, there exists some x comma y in the region R such that f of x comma y has a minimum value. There's something strange about mathematics, especially as you get into higher level courses. The simplicity of a theorem is basically no indication of the simplicity of the proof. This statement seems very simple. Okay, you give me a function. Yeah, I can find somewhere where it's maximum, somewhere where it's minimum. The proof of this is very far beyond the scope of this course. Graduate level, like graduate school, graduate level analysis would be appropriate. This would be an appropriate problem. So here, the proof of this, we're going to just go ahead and take advantage of the result. The proof is left for more advanced classes. We're not at the level where we could do that. Or apparently spell that. There we go, advanced courses. So here we're going to just take advantage of that statement without actually proving it. Okay, so here, this is a proof of existence, or rather, theorem of existence. We don't really have a proof here. A theorem of existence which states, okay, we're not telling you how to find it, but we're telling you as long as your region is closed and bounded, we guarantee you that you will find one. Okay, all right, so now, well, if I know I can find one, can you be more specific? Can you tell me where to find it? Well, sort of. Let's go ahead and state the next definition. Let's have a function f of two variables. Let f of x comma y be defined on an open region R which contains some point. Which we'll call x naught comma y naught. Okay. That point x naught comma y naught is called a critical point. You may remember the name critical value from Calculus 1. The critical point of the function f if either of the following is true. If f sub x at x naught comma y naught is equal to f sub y at x naught comma y naught equals to 0. So it's called a critical point if the two partials are equal to 0, or if either partial is undefined. Let's say does not exist. So either they're both 0 or at least one is undefined. They don't both have to be undefined, but at least one. But if you're going this route, they both have to be 0. Okay, so it turns out that we're defining critical point. It turns out that our critical points can help us locate our maximums and minimums. Now, they're not exactly the same. However, they are strongly correlated. Which we see with the following theorem. Okay. If a function f of x comma y has a relative extrema, relative extrema at the point x naught comma y naught, then x naught comma y naught is a critical point of f. Note that does not say that if you have a critical point, it is a relative extrema. It's saying if you have a relative extrema, then it has to be a critical point. What that means is you might have 20 critical points, but only 2 of them are relative extrema. Right? It doesn't mean every critical point is a relative extrema. It means that if you have a relative extrema, it had to have been one of the critical points. Right? So if you have 20 critical points, you might only have 3 relative extrema. Oh, but those 3 had to come from the list of critical points. So be mindful of that. It only works in one direction. Relative extrema must be critical points. Just because something is a critical point does not mean it's a relative extrema. The proof of this is a lot more accessible than the proof of the previous theorem. Let's see here. So there's really 2 possibilities here. Based off of what we mean by a critical point, it could either be that the partials are undefined or the partials are both equal to 0. Okay, well, let's consider the first one where the function is does not have defined partials. If the function is not differentiable, at an extrema, then at least one of the partial derivatives, f sub x or f sub y, does not exist. Okay. So let's say I found a relative extrema of a function. Well, then there's two possibilities. One is that at the relative extrema, my function is not differentiable. Right? Just because it's not differentiable does not mean that I don't have an extrema there. Oh, but if it's not differentiable, then that means that at least one of the partials does not exist. So that means that at the point, I have a critical point. So the extrema is a critical point. Okay. Okay, well, what if it is differentiable? All right, well, then let's see. On the other hand, so here I'm proving this in two parts, 1 and now 2. If the function is differentiable, those are the only two possibilities, right? Either it's not or it is. Okay, so if the function is differentiable, let's see here. At a relative extrema, at a relative extrema x naught comma y naught, then, okay, well, if it's a relative extrema, that means it's a relative extrema relative to all of its directional derivatives. Right? If that's a relative extrema here, that means it doesn't matter which path I go, that has to be an extrema of this curve, and it has to be an extrema of this curve and this curve. Every path that I take, it would have to be an extrema of that path. Oh, but each of those paths are just curves on a plane. And we know from Cal 1 that if you have a maximum or a minimum, that's the first derivative is equal to 0, right? Assuming it's defined. Okay, so then that means that no matter which way I go, my line that is tangent to my curve at that point forms a perfectly flat line. A perfectly flat plane. Every one of those tangent lines has a slope of 0. So if it's at a slope of 0 in every direction, this is a perfectly flat plane, meaning it's parallel to the xy plane. So if the function is differentiable at the relative extrema, x naught comma y naught, then the plane tangent to the surface z equals f of x comma y must be horizontal to the surface at the point x naught comma y naught is horizontal, by which I mean parallel to the xy plane. Well, that means, the way I drew over here, that means that every directional derivative this means every directional derivative d in the direction of u of f at x naught comma y naught has to equal, which is equal to f gradient dot u, is to equal to 0. Every directional derivative must be 0. But of course, one way of defining the directional derivative is the gradient of f dotted with the direction u. And this is going to be true for, since it's for every directional derivative, for all u. No matter what direction we're going in. But then that means that the gradient of f dot u is equal to 0. And since u is not going to be 0 because it can be anything, then that must mean that the gradient of f is equal to 0. But if the gradient of f is equal to 0, since the gradient of f is equal to f sub x comma f sub, that should be 0 vector, f sub x comma f sub y, then the only way for this to be the 0 vector is if both of these are 0. So that means f sub x is equal to f sub y. It should be at that point. So f sub x at x naught comma y naught, because this isn't generally true, it's true specifically at that point, is equal to f sub y at x naught comma y naught, which is equal to 0. In order for this to be the 0 vector, both components must be 0. But by definition, that means that my derivatives are both equal to 0 at that point, so by definition, that must make that a critical point. Therefore, the extrema is a critical point. So there we go. It doesn't matter if your function is not differentiable or if it is differentiable. Either way, the extrema is a critical point. But those are the only two possibilities. Okay, so then no matter what, the extrema must be a critical point. And that proves our statement. So this theorem tells us where we might find our relative extrema, but it doesn't tell us exactly where. It only tells us, okay, we've cut it down to just this. If you can find your critical points, then out of those you can find your relative extrema. That doesn't really tell us which ones though, it just sort of narrows down the list. So for our last theorem for this section, we'll see how we can use what's called the second partials test. This is reminiscent to the second derivative test in Cal 1 to actually confirm which of our critical points are relative maximums, relative minimums, or one other thing which we'll call a saddle point, as we'll see here. Theorem. And this one actually has a name. We're going to call this the second partials test. It's like the second derivative test. All right, we're going to begin with a function of two variables. Let f of x comma y have continuous second partial derivatives. Second order partial derivatives on an open region which contains some point. Which we'll call AB. All right. That AB is such that the first partial with respect to x at AB is equal to 0, and the first partial with respect to y at AB is equal to 0. In other words, it's a critical point. Finally, let D, the number D, be given by the second partial, both with respect to x, of f at AB, times the second partial, both with respect to y at AB, minus the square of the mixed partials at AB. Right. If you define D as the product of these two minus the square of this one, it's going to give you a number, assuming you've plugged in your point. Then the following possibilities may arise. If D is greater than 0 and f sub xx at AB is also greater than 0, then f has a relative minimum relative min at AB. If D is positive and f sub xx at AB is less than 0, then f has a relative max, a relative maximum at AB. If D is less than 0, then the point A, comma B, comma F at AB is called a saddle point. A saddle point is a point that looks like a minimum in one direction, but a maximum in another direction. So for example, here we see a maximum, right up there, a relative maximum. Here we see a minimum, well, a relative minimum. But a saddle point, it looks like it would be a maximum in one direction, but a minimum in another direction. So here the stuff in gray is meant to be the inside, and the stuff in blue is meant to be on the outside. So it's sort of like a tunnel. Notice at this point, if you walk in this direction, it looks like you're going uphill. So that really does look like a minimum. But if you start walking in, let me try not to destroy my camera. There we go. If you start walking in this direction, well, you'd be going downhill. So it looks like it's a maximum. So it's a minimum in one direction, but it's a maximum in another direction. That's called a saddle point. And finally, if D is equal to 0, then this test is inconclusive and, well, you learn nothing. You learn nothing about the surface. Just like our first theorem, the proof of this one is omitted due to being a little more advanced than what we're prepared to do. So proof is omitted due to being very, very scary. But that doesn't sound formal enough. So I'll say omitted and is left for a course for a course in advanced topics. In other words, too scary. So here, just like the first theorem, we'll simply take advantage of the results, and the proof is left for later courses. So let's take a look at some examples. Let's identify the saddle points and relative extrema I guess there's one. And relative extrema of the function z equals x squared plus xy plus 1/2 y squared minus 2x plus y. All right, so here we go. First of all, we want to find all of our first and second order partial derivatives. All right, so here z equals this. That's another way of saying f of xy equals this. So here we're looking for f sub x. Well, let's see. That's going to be the derivative with respect to x of all of this. It's going to be 2x plus y. That one will have a derivative of 0. That'll have a derivative of minus 2. And that'll have a derivative of 0. Okay. All right, and then we can look for our derivative with respect to y. The derivative with respect to y, that's going to be 0. That's going to be x. That's going to be 1y. All right, so 0x, y. Derivative with respect to y of that one is 0. And the derivative with respect to y of this one is 1. Now we're going to look for our partials. Let's look for f sub xx and f sub xy, f sub yx and f sub y, y. All right, the derivative of this with respect to x is a constant value of 2. With respect to y is a constant value of 1. With f sub y, you have x plus y plus 1. And if you want to take the derivative of that with respect to x, well, that's just going to give you 1. And if you want to take the derivative of that with respect to y, that will also give you just the value of 1. Now, we can find the critical values by looking at the first derivatives. Okay, so first of all, let's find critical values. Let's see. First of all, we want to find, are either of these ever undefined? Well, they're polynomials, so no. Neither f sub x nor f sub y are ever undefined. Okay, so then we don't have any critical points from that. But it does look like we can make them equal to 0. Right? So here, now remember, we need them both to be 0. 2x plus y minus 2 equals to 0. Simultaneously, x plus y is equal to 0. Sorry. X plus y plus 1 is equal to 0. And here, this is a system of equations. We want to solve both of them equal to 0 simultaneously. So here I can go ahead and subtract the two lines from each other. 2x minus x is equal to x. Y minus y is 0. And negative 2 minus 1 is negative 3. And 0 minus 0 is equal to 0. So then that suggests that x must equal to 3. And if 3 plus y plus 1 is equal to 0, or of course I could do for the top one as well, but this one works just as well. If 3 plus y plus 1 is equal to 0, well then y must equal to negative 4. So it looks like that gives us our only critical point. Critical values, that should be critical points. Critical values are when you just have a single value, like x equals something. That's the way we do it in Cal 1. But here, we're looking for critical points. It's got an x and a y. So find critical points. All right, well, in that case, we have just a single one. There was never a place where they were undefined, but there was a single point where both of those partials were 0. And that was 3, negative 4. Okay, so now let's go ahead and test this using our previous theorem. We're going to go ahead and find the value of d. Now, as we saw, we defined d. We're going to take the second partials. We're going to plug in our critical value. We're going to take our second partial, plug in our critical value. We're going to find our second partial, plug in our critical value, square and subtract. So let's go ahead and give this a try here. D is equal to f sub x at 3 comma negative 4 times f sub y at 3 comma negative 4 minus f sub xy, or f sub yx, those are the same, at 3 comma negative 4, and then this last one here is squared. All right, so let's see. Note that in this case, all of these are constants. So here we'll just use the constants. If they were not constants, of course, you would just plug in those values, the 3 and the negative 4. All right, if this was 2x, well, you'd plug in your 3. If it was 2x plus y, well, then you'd plug in your 3 and your negative 4. But here, since they're constants, there's nothing to plug in. So f sub x is going to be 2. F sub y is equal to 1. So 2 times 1. Minus f sub xy, that's also equal to 1. And that second term is squared. So that'll give us 2 minus 1, which is 1. All right, so it looks like we have a value of d, which is 1. And what matters is that it's positive. Here, d is, we're going to distinguish between whether it's positive, that'll give us an extrema, negative, that'll give us a saddle point, or 0 gives us nothing. Okay, well, that's greater than 0. So this is going to be an extrema, either a maximum or a minimum. The way we determine whether it's a maximum or a minimum, once we know that d is greater than 0, now we need to look back at the first, partials with respect to x, second partial with respect to x, f sub xx. If that's positive, you have a relative minimum, because that means the whole thing was bending up this way, so it's a minimum. If f sub xx is negative, well, then the whole thing is bending down, so that's a maximum. All right, well, let's see over here. We have d is greater than 0. We have f sub xx at that point. Well, again, it's a constant, so we don't really worry about plugging in anything. If there were an x or a y here, you'd plug them in. But here, f sub xx is equal to 2, which is certainly a positive number. So you have d, which is positive. You have f sub xx, which is positive. So that means that we have a relative minimum. And since there was only one critical point, well, then there could only be one, up to one extrema. So here we find that the one critical point actually does turn out to be an extrema. And now we get that we have f has a relative minimum at 3 comma negative 4. Right. And that's our result. Right. You may wish to try this. So let's go ahead and see another example here. Let you try this out. Identify any saddle points. And any relative extrema. Make sure you label it a relative maximum or a relative minimum. Of the function f of x comma y is equal to 2xy minus 1/2 x to the 4th minus 1/2 y to the 4th plus 1. Okay. Nothing tricky here. Same thing. You're going to go ahead and find all of your first and second order partials. You're going to find the critical points. You're going to find d and then discriminate your critical points into either saddle points, relative extrema, or nothing, and throw those away to find your result. Go ahead and pause the video, give this a try, and once you're done, go ahead and unpause and we'll go through it together. All right, so we're going to start by taking all of our partial derivatives. Let's start with the first order partial derivatives, f sub x at x comma y. Now let's see, the derivative with respect to x, that'll be 2y. That would be 4/2 x to the 3rd, or in other words, 2x to the 3rd. Here, the derivative with respect to x of these is just 0, since they're constants with respect to 0. F sub y at x comma y, the derivative with respect to y would be 2x. These would be 0 since they're constants with respect to y. And the derivative of minus 1/2 y to the fourth with respect to y would be minus 4/2, in other words, minus 2 y to the third. And now from here we can find our second order partials at x and y. Note here you don't need to find them both, assuming they both exist and are continuous. These are going to be equal to each other. So here if you can find one or the other. I'd go with this one, but either one's fine. Here, f sub x, that's going to be the derivative of this with respect to x, which will be 0 minus 6x squared. The derivative of this one with respect to y, well, that'll be 0. So really just the derivative of this part, which is the number 2. Here, if I take the derivative of this one with respect to x, again, that's just the number 2. So again, you'll notice these are equal to each other. As long as they both exist and are continuous, we expect them to be equal to each other. And finally, f sub y, the derivative of this one with respect to y would be 0 minus 6y squared. Like that. Okay, so now we're going to go ahead and find our critical points. All right, critical points. First of all, we want to find if these are the first partials are ever undefined, and again, they're polynomials, so no, they're not. F sub x at x comma y and f sub y at x comma y are never undefined. If either of them was undefined, well, then you'd have a critical point at whatever point those are undefined. But since that doesn't happen, these are never undefined. And so you never get any critical points from that. On the other hand, you may get critical points from having both of them equal to 0. Right, here, if either is undefined, that's a critical point. But they both have to be 0 for that to be a critical point. So that's going to be 2y minus 2x cubed equals to 0. And 2x minus 2y cubed is equal to 0. So let's see, we can't solve that system of equations. First of all, let me go and divide everything by 2 because, well, why not, right? Y minus x cubed equals to 0. And x minus y cubed is equal to 0. Here I can easily solve for one of my variables. For this bottom equation, I can always say x is equal to y cubed, moving that over to that side. But now I could take that and substitute that result into the other equation, right there, which will give us a single equation, y minus y cubed is equal to 0. Y minus, since x is y cubed, that replaces that x, which is then being cubed, equals to 0. So I'm left with y minus y to the power 9 is equal to 0. Okay, well that can be solved. That can be factored as y times 1 minus y to the 8th equals to 0. Here, if I have y is equal to 0, well then that's my solution. So y is equal to 0. If I have 1 minus y to the 8th is equal to 0, well that means y to the 8th is equal to 1. Right? 1 minus 1 is 0. So if y to the 8th is equal to 1, assuming we don't want any complex numbers, right? We're not gonna pull the roots of unity like we would in trigonometry. Here we're just looking at the real solutions of that. What numbers can we raise to the 8th power to give us 1 or to give us 1? Well, that's going to be 1 or negative 1. All right? Negative 1 to the 8th is 1, minus 1 is 0. Positive 1 to the 8th is 1, minus 1 is 0. And 0 times anything is 0. So it looks like I have 3 solutions for y. So now I can take those and plug them into my substitution to find my values of x. So if x is equal to the cube of y and y is equal to 0, well that means x is equal to the cube of 0. In other words, x is equal to 0. If y is equal to 1, then x is equal to the cube of 1, which means x is equal to 1. And if y is equal to negative 1, that goes in there, that means x is equal to negative 1 to the power 3, which is still negative 1. Okay, so it looks like I have no critical points from this statement, but I have 3 critical points from this statement. It looks like my critical points are 0, 0, 1, 1, and negative 1, negative 1. All right, so now we're going to go ahead and find the value of d. And now remember, d is equal to, well, we have 3 different values for which we need to find d. So let's go ahead and try all of them. At 0, 0, d is going to equal to f sub x, x at 0, 0 times f sub y, y at 0, 0 minus the square of f sub xy at 0, 0. All right, so let's see what that is. If we take f sub x, x, it's going to be negative 6 times x squared. You plug in a 0 for x and y. Well, there's nowhere to plug in y, so you just plug it in for x. That's going to give you 0. If you take f sub y, y, and plug in 0, 0, well, there's nowhere to plug in x, but you can have y is equal to 0. The whole thing is 0. Minus, you're going to take f sub xy and plug in 0, 0. Okay, well, there's nowhere to plug in 0 here, so just take your constant, 2. And the whole thing is squared. Okay, so that's going to be 0 minus 4. That's equal to a negative 4. Oh, but now that tells me that since d is negative 4, it's less than 0. When d is a negative, then automatically you have a saddle point. So here we're going to have a saddle point. We don't need to check anything else. At 0, 0. Let's try the next one. Let's try 1, 1. Well, then d is equal to f sub x, x at 1, 1 times f sub y, y at 1, 1 minus f sub xy at 1, 1. And that last term is being squared. So f sub x, x, I'm going to plug in 1 for all my variables. Okay, well, if I plug in a 1 right there, that's going to be negative 6 times 1. That's a negative 6. F sub y, y at 1, 1. Okay, well, here's my f sub y, y. If I plug in a 1 right here, that's going to be negative 6 times 1, which is negative 6. Minus f sub xy at 1, 1. And it doesn't matter what point you're plugging in because notice f sub xy is a constant. It's the number 2. So no matter what you plug in, it's the number 2. But don't forget that's being squared. All right, well, that's going to be negative 6 times negative 6 is a positive 36. Minus 4 is a positive 32. But since d is 32, which is positive, that's going to give us a relative extrema. Okay, so now we need to check. So this is going to give us an extrema. Okay, now which extrema? Oh, well, then we need to now go back and double check f sub x, x. Since f sub x, x at 1, 1 was equal to negative 6, and that negative 6 is less than 0, then we have d is positive, but f sub x, x is negative. D is positive, but f sub x, x is negative. That means we have a relative maximum at that point. So we have a relative max at, what was the point? 1, 1? At 1, 1. Okay, so far we have one saddle point. We have one relative maximum. Now let's see what the last one is. If we plug in negative 1, negative 1, well then d at f sub x, x of negative 1, negative 1 times f sub y, y at negative 1, negative 1 minus f sub xy at negative 1, negative 1 quantity squared. All right, let's give that a try. If we plug in -1 into f sub x, a -1 goes there. Square that is now a +1 times -6 gives us -6. F sub y will look the same. Here I'll plug in a -1. -1 squared is +1 times -6 gives me a -6. And then f sub xy, again, just like every time we've seen so far, that's a constant. F sub xy turned out to be a constant for this problem, so it doesn't matter what you plug in. It's always the number 2. So this is the same as before. 36 minus 4 is 32, which is greater than 0. So you know that's going to be an extrema. Okay, now which extrema? Well, again, going back to looking at f sub xx. If you look at f sub xx at -1 comma -1, well, we saw that was -6 right here, which is less than 0. So it repeats the same results. You have an extrema. Here, your f sub xx is negative, so you end up with a maximum. So that means you have another relative max at the point -1 comma -1. Even though the question does not ask us to graph in any way, let's go ahead and take a look at what the graph of this would look like. Here, without going into too much detail, and just using the results that we get from this from this test here, here you would have a saddle point at x equals 0 and y equals 0. Incidentally, you can always check where on the graph that belongs by just plugging those in. So here, if x and y are both equal to 0, you go back to your original function, and that gives you 0, minus 0, minus 0, plus 1. Okay, so 0, 0, 1. Right about there. That's going to be a saddle point. Okay. At 1, comma 1, well, again, you could plug in 1, 1 into all of this, and that would give us 2 minus a half minus another half plus 1, which gives us 2. So this would be 1, comma 1, comma 2. So this would be a little bit higher up over here. And if you plug in -1, you're going to get the exact same thing. It's going to be 2 minus a half minus another half plus 1, and that will also give us 2. So even though you're on the other side over here where x and y are both negative, you'd end up still with the same height of 2. So that's a height of 1, that's a height of 2. So our graph looks something like this. It's going to come down to this point and up to this one. Okay, so like this. But then that really does look like it would be a relative minimum. Oh, but it's a saddle point. So it should look something like this, where it looks like a minimum from one side, but it'll kind of look like a maximum from the other side. So something like that. Here, these will actually be like little hills. So if you were going to draw some level curves, here this would be at the same level, this would be at the same level, like this. Like that. So you would have one maximum here at, let's see, this would be what, -1, comma, -1, comma 2. You'd have another relative maximum over here at +1, comma 2. And then here was 0, 0, 1. And we see that that's a saddle point. This is just a very rough sketch, but just from this information, that's a pretty decent sketch from a mathematical standpoint, certainly not from an artistic standpoint. So that brings us to the end of this section. If anybody has any questions, comments, or problems on any of these, please go ahead and make a note of those, reach out, and I hope everyone has a nice day.